Thank you. It's an honor, it's a privilege to give a talk here. This is the first talk I've given at MIT in about 41 years. So, and I hope the norms have not changed. That is to say that I won't, do things or say things that will make people run screaming from the room. As an xTalk in a general field of open learning, I think there's a number of issues I want to discuss. The first part will be about learning in general, and the second part will be about the specific approach I've taken to help learning with the use of modern technology. And it may be an xTalk, but as my name is Ted, that means, of course, this is also a... All right. As Molly said, I have worked for a number of years, almost 38 years, at the Delft University of Technology in the Netherlands, which don't know where that is, it's okay. It's right near The Hague. It's in between The Hague and Rotterdam. And it's interesting because in the Dutch language, unfortunately, in my feeling, there are no separate words for teaching and learning. That gives problems, I think. It identifies something right away about how you view the process. And as I view the process, I very much appreciate the concept that there's teaching and there's learning. There's a protagonist and an antagonist. There's two sides involved in it, not just one word. And I'm old school. Well, you knew that right away when you looked at me. But I'm old school, and I really mean it, because the school that intrigues me the most, and I think has the most to offer, is about 2,400 years old. And that's the Socratic method of teaching. And in the Socratic method of teaching, which I read when I was a freshman at MIT, it was in the freshman curriculum, reading Plato, reading Socrates or the Plato dialogues, was the nature of the interaction between two people and asking pointed questions to bring out an idea and then explore it and develop it, constantly challenging the person who's being asked, the Socratic method. And when we went to put together, and I say we, and I'll explain that in a second, when we went to put together a textbook that would be running on a modern digital device, you are required when you put these things up on an app store, you put them up on the Google Play Store, you are required to have an organization. Among other things, you have to have a domain name. One of the reasons is because somewhere on the world, you have to have your policy about privacy. And that can't be in the app itself. It's got to be external. So we have to think up a name for that particular domain name. And our domain name is Socratic Software, just to not put too fine a point on it. And so in the Socratic method, we ask a lot of questions. And that will come back in the app. Right? But we're not really it wasn't just the Western civilization, Western culture, in this case embodied in Socrates of 2,400 years ago. Let's see, am I going to get right in? Yeah. It was, the Chinese have known about this for a very long time. They have a proverb that addresses this issue. That here's the app, okay? And so you click on this. We all know how to do this kind of stuff. This is not hard. I really wanted to click on this, but I've only worked one room that actually had that, but this is not it. Okay, so here it is, and this is the start of the book. This is called a flash screen. And then it goes over to here, and there are various components to it. In the upper left-hand corner, those bars, you're all familiar with them. It's a standard symbol. The menu will drop down. The name of the textbook is Introduction to Stochastic Signal Processing, short iSSP. That was the name we wanted for the book. That it coincidentally corresponds to iPhone, iPad, iMac, and the rest is actually just that. It's a coincidence. I think we would have called it iSSP, even if all those other devices had not already been put forward, in that case, by Apple. And the person I've worked with on this is Ronald Lichteringe. We make very heavy use of some very difficult stuff inside in this case, the iPad. And while the text for the textbook was written by myself, and the homework problems and the laboratory exercises, stuffing them into an iPad, in this case is about 60 megabytes. The book is 60 megabytes, including everything, is something that he is very, very good at doing. But there's another way to get around. You can just go over to use this ebook. You just go down here to go from chapter to chapter 1. Here's chapter 1. And here in the upper right corner is this proverb from the Chinese, which says, to hear is to forget. Meaning, of course, that everything I say now you will forget when you leave the room because you're hearing it. And that's okay. That's okay. I recognize that that's a risk. The second thing is to see is to remember. So the visual stuff on the screen sticks for some reason perhaps better in your memory than the auditory things. And the last one is to do is to learn. To be involved, to answer questions is to learn. So the learning process is not just aided, the learning process requires this interactive component to make things that you know and not things that I'm telling you. And so that's how we got started in all of this. My mother passed away a number of years ago. She used to say the same thing. She said, you can't teach people anything. I thought she was being cynical. If you knew my mother, that was a possible interpretation, especially when she knew me. You can't teach people anything. Later I came to realize you can't teach them because they have to learn it on their own. So that's another way. So along with Socrates and the Chinese proverb is my mother. And finally, there was Professor Irwin Corey. Has anyone here ever heard of Professor Irwin Corey? Of course not. Most of you never heard of him? No? You've heard of Professor Irwin Corey. Yes, of course. He was the world's foremost authority, right? Period. Okay? And you can go Google Professor, go to YouTube, Professor, and he would pontificate on just about anything. But at the end, he would then say, but what does it mean? Now, it took me a long time to catch on that that's a key question. And frequently in the results that we talk about in the book, I actually pose the question, what does this mean? Not that just you could add and subtract and you can filter and you can restore and you can do all kinds of things. What does it mean? And that's the kind of question that's involved in this Socratic method. Okay, then moving along, let me ask you, let's consider the, I can spring to the bottom of this and go back to here for now. Hello, go back to here for now. Okay, next. Inspiring education. There are inspiring teachers, and if you've had an inspiring teacher, you know how important that is. It can change your life. Perhaps the most inspiring teacher I ever had was here at MIT when I was an undergraduate, and that was Professor M.R. Bose. And Bose was, you may know him, the younger among you, from Bose speakers and Bose audio equipment and so forth, but I was fortunate to have him as a teacher in a sophomore course in the electrical engineering department in introductory network theory. The fact is, it would not have mattered what he taught. He was an inspiring teacher. One of the people here also had Bose as a teacher at some point in his education. And that sticks with you. And if you've had inspiring teachers, you're lucky, because most of us go through and you say, well, name the inspiring teachers, and the first thing you have to do is sit down and think, who were they again? You certainly had a lot of teachers, but how many of them would you put up there with after the name, say, inspiring? And okay, then that brings us to the question, if the person can be inspiring as a teacher, can a piece of software be inspiring? Can a book in an iPad be inspiring? Can it cause you to really learn something in a way that you say, I never would have gotten to that material if I hadn't had this teacher, computer program, video learning demonstration, and so forth? The first one I can prove, to the extent that I've experienced it myself. I was thinking about this question for a number of years when I got inspired to do this. And I'm not saying that what we've developed is inspiring. I want to know, do other people find it inspiring? That would answer the question, can digital education be inspiring in and of itself? Can online education be inspiring? That is not a trivial question in the context of these xTalks. And I'd say, well, why would I not think so? Well, I think personal contact is necessary. When I look out in this room now, I can see people's faces. I can see if they are following what's going on. I can see if their faces are blank and they're lost or they start reading a newspaper. There's an immediate feedback to me as to whether I'm communicating properly. I've also had the opportunity in the past to teach a course to a camera. And it was recorded and it was available to students, and it was impossible. Well, you had to get over it and you had to go and do it. And it was a course in thermodynamics and statistical mechanics. So I give this course and I'm giving these lectures, and there's nobody out there to let me know if I'm doing it right, to tell me if the ideas are getting across. So this contact in one direction. Secondly, there's nobody in the audience asking me questions, because they're out there in Never Never Land, and there's no feedback to me by saying, I didn't understand that, could you explain it another way? Or you made a mistake on the board. Is that a mistake, really? Or did I just misunderstand something? That back and forth between the teacher and the student was important, at least to me, in the process of trying to teach, and I think to them in the process of learning. You also get in education, we've seen increasingly how important it is that people work together in groups, in teams, and it's encouraged. And MIT, for example, is heavily involved in a program called MEET, M-E-E-T, which means Middle Eastern Entrepreneurs for Tomorrow. And it's going on in Jerusalem, and MIT provides teachers for this, and they take groups of young people in high school, and they bring them together, and the ground rules are, for every young man, there's a young woman, so it's 50-50, and for every Israeli Jew, there's a Palestinian Arab. And so the smallest number of people in a group would be, it's an MIT question, 2. You could have 2 people, and that would meet all the boundary conditions. But generally, the groups are either 4 or 8. It depends on the nature of the projects they're working on. And, but they work together, and they bounce ideas back and forth, and they criticize one another, and they share frustration when they arrive late because they were held up at a blockade or something like that. They work together. That teamwork seems to be essential in many learning things and a lot of projects that go on in life, not just in industry, but in life. And so that seems to me an important part of making progress. There are other things being offered. There was an xTalk offered, I think in February here, by someone named Michael Yoffe. And he was talking about education by texting, right? I don't know if any of you were there, but he said, I guess I'm quoting now, text messages are the next frontier in digital education. I don't agree. I'm understating my objection to that. Let me put it this way. Education is associated with texting the way governance is associated with tweeting. Okay. Back to the issue. Can educational software be inspiring? Well, my inspiration for this project came from an unexpected direction. It was about 10 years ago that Steve Jobs introduced the iPad. Now, I don't know if you ever saw any of his introductions, but he'd get up there and he'd talk about all kinds of new things that Apple was doing with existing products. Updating the operating system, adding a better camera, adding a better lens on a camera, a whole bunch of stuff. And then at the end of the talk, he'd say, what'd he say? One more thing. I thought he learned that from Columbo, but that's something else. One more thing. And then he'd launch a new product. Now, he launched a lot of products. The personal computer kinds of things in the Apple model. He launched the iPod, he launched the iPhone, he launched Apple Music, he launched the iPad. So he's presenting this iPad, and at a certain point he puts the screen up, like I've got a screen up here, but what he's showing is the front page of the New York Times, because they'd worked it out with the New York Times that it would be available online, and so here you see the front page, and you look at it and you say, yeah, that's the front page of the New York Times, and there's the story that was that day and everything, and he says, and you know, we've been working with New York Times, and it's going to be available, and you can have a subscription, etc. And of course, in the New York Times on the front page, there's a picture, right? Now, I read the New York Times, I've seen the pictures. And then he taps on the picture and it starts to move. And I was blown away. When that happened, I said, I could write a textbook in which the images were no longer static. And in fact, if the images weren't static, there could also be sound that you could listen to. Suddenly, it became a dynamic medium instead of a static medium. And this all happened to me in this sort of epiphany. And that was the beginning of trying to put this whole project on an iPad. Now, the funny thing is, and this is also true for many cases in education, I could have sworn it was Steve Jobs who did that. So I went back on YouTube and I tried to find that moment on YouTube. And the only thing maybe it's me, the only thing I can find is not Steve Jobs at that moment, but somebody else from the Apple Corporation doing it. But to this day, I swear it was Steve Jobs doing it, showing that memory can be tricky, but the experience was genuine. Okay. And thus, let me put it this way, that was an inspirational video. It can happen. So when you see it. That brings us to the issue of classic textbooks. Classic textbooks are wonderful. I use them. I still have them. I still use them as reference books. I wrote one with Al Oppenheim and Al Wilsky here at MIT, Signals and Systems. Came out in '82, I believe, something like that. So it's been out for many years, almost 40 years, and it's still available. They're very good, but they're static, they're permanent, they don't change. If there's an example in there that was relevant in 1982, today people might look at it and say, oh, that's such old technology they're describing. What you'd like to be able to do is update things. You'd like to have a dynamic medium, not just for the movies, but so the content itself at an appropriate time can be updated. Video lectures, as this is going to be when you've finished recording and it's going to be put up on the web, will again be one-way and not two-way. Okay, so even there's a little bit of a lack of being able to engage this two-way conversation between the student and the person who's presenting material. To get over that, we chose the ebook approach. Now, if you go look at ebooks in general, they're wonderful. That's where I do a lot of my reading these days because I can make the letters big. But they also do not admit, as of this time, incorporating some of the technology that's in an iPad. I'll give you an example. An iPad has a microphone. You can't, in an ebook format, get to the microphone. You can play a sound out of the speaker, but you can't get to the microphone. And we wanted to get to the microphone. So now I got to see it. Okay. So what would our app have? What would our thing? Well, it wouldn't be an ebook. It would be an app, a genuine app. The way you saw, I launched it by clicking on the icon. And in that, we could then have film clips. We could have animations. We could have sounds and so forth. Plus, we could have laboratory exercises. And that's where the interactive part really comes to the front. We can have experiments that you do as if you were in a laboratory using the iPad, and I will show you some of those in a little bit. All right, so let's start off by going first to show you the textbook part. So we'll go, here's the menu of all the different chapters, and as you can see, there are 12 different chapters, plus appendices, plus some information like the ISBN number and a bunch of other stuff. You can also find the version number of this particular thing. And that's another thing, it'll update itself automatically. If I upload something to the App Store, then within about 24 hours, within 24 hours, I usually get back a thing that says, it's for sale. The price right now is $0. So then you download it, okay? And once you're in the ring, in the loop, every time I get an approved one from them, you'll get an automatic update. So I don't have to send you a note and say, you can update it now. But let's go to chapter 4, characterization of random signals. And this is what a chapter looks like. And pretty much what you might expect in any textbook. I'll be honest with you. We can do color liberally because we don't have to pay for printing costs. So that's an advantage. But you can see it looks like text and a graph and an equation. And it just starts going down, describing the ensemble settings, an example of what is an average, more equations, average expectations, and so forth. And it just keeps going down. And in a sense, this part looks like what you would see if you took a book off the shelf from one of the libraries, an old-fashioned book, except it's here and it's not on paper. Of course, you can do that if you want. And you'd say, why will I want to do that? Well, maybe the equations might be easier to read if you do that, but that's not necessary in general. And goes into a number of different topics. It's all chapter 4. And then we get down at the bottom of chapter 4, and we start getting to the problems, the homework problems. And in this case, there are a bunch of homework problems. Right now, there are, let's see how many, 9 homework problems, followed by laboratory experiments. In this case, 2. Now, the version of this app that is currently available from the App Store has 26 experiments, but I have designed 62, and the others will become available over a question of time. In fact, there is a 4.3 already, but I'm going to wait till I finish all of the experiments for chapter 4 and then upload them all at the same time. And then we'll go to version 1.2 of the software. But it takes time to translate an experiment that was designed in Mathematica to one that is now running in JavaScript and is running on an iPad. I mean, there's a lot of work I got to do, and that's why it takes time. Okay, that's an example of the textbook. Now let's go look at another facet. We're going to go look This is a chapter on the Wiener Filter. I don't know if any of you know who Norbert Wiener was, but he was a professor here at MIT, a mathematics professor, one of the great mathematicians of the 20th century. He died in 1964. I actually met him once when he was in the infirmary here near Building 10. And he was, well, ask somebody who's been around MIT a long time to hear some Norbert Wiener stories, because he was the prototypical absent-minded professor. And all of the great absent-minded professor stories are based on Norbert Wiener. Maybe afterwards I'll tell you one. Okay, so what we're going to look now is, go to the bottom here. Let's see, Wiener Hoppe. Oh no, I know what to do. You can go here, and then in chapter 10, where it says the Wiener Filter, you now notice there's some bars, horizontal bars next to it. I click on that, and then it says here are all the subtopics in that chapter. I'm going to click on the Wiener Hoppe equation. It should have gone through the Wiener Hoppe equation. I don't see that it did, but okay, here's the Wiener Hoppe equation, and then, come on, don't give me a hard time. I'm in front of all these people. Okay, here's the Wiener Hoppe equation, and you'll notice that Professor Norbert Wiener, 1894 to 1964, it's in a different color. It's a link. And if you click on that link, come on. It jumps. This is Wikipedia's fault, not mine. That's the picture they've managed to put up of Norbert Wiener. Right? He forgot to send the rest of the picture. But anyway, you can get information about this person. So one of the things you can do in a book is you can make links to the outside world, which is nice for doing several things. One of them is to round out the information you have perhaps about someone very famous like Norbert Wiener or Nyquist or Shannon or whoever, or Wolfgang Pauli, for example. And so it extends the range of your information gathering in an almost painless way. And then you can go click in the upper left-hand corner. You'll see iSSP up there, and I'll click on that. And you go back to where you were, as you might expect. And then also, if you go to chapter 11, okay, we're going to chapter 11, which is called Aspects of Estimation. And right over here, something called the Pythagorean means. Pythagorean means. I don't know if you know what they are. It's not that important. There's the arithmetic, the harmonic, and the geometric mean. They're relevant for this chapter. But if you want to know more about them, you click here, and Wikipedia comes up, and it's not just reading biographies of people. If you want to dive into the depth of some of the mathematics, you can pick up sources like Wikipedia or others. Okay. That is the example of links. Then there's the example of audio. So for that, we'll do two examples. We'll go to chapter 1. And now we're going to hear a fragment of music that I cut out of a piece of recorded music. And then I processed it to make an example. But the very first time you hear it, it's just being presented for the first time to show in chapter 1 that your iPad can play music. You can interact and make it play music. So it's a small fragment from Paganini. Okay? Now we'll go to that processed. That's going to actually be processed in chapter 10. Okay, and that's chapter 10 right above the problems. So right before the problems begin in chapter 10. Okay, you've heard the piece of music. Now one of the things we talk about in this textbook on the processing of random stochastic signals is signals get noisy. How can you remove the noise? Signals get distorted by bad recording, for example, with a bad microphone or a bad amplifier or in a room with bad acoustics. Is there a way that you can improve the quality? And one of the techniques people use is Wiener filtering to improve it. And here's an example. Now you're going to hear that exact same piece of music, but distorted by a bad filter and noisy because the ambient noise in the room was gigantic. Okay, same piece of music, but you wouldn't want to listen to it. Now we apply the Wiener filter, and this is the result. Not perfect. You can hear all kinds of things there. He said that wasn't in the original, but certainly much, much better than the thing before it was processed. And that's to give the students the idea of, we've just talked about a whole bunch of mathematics. What does it mean? What does it let me do that I couldn't do before? What could I listen to that I couldn't hear before? And of course, supporting that are laboratory experiments. It's not just this. Here, it's pre-cooked. I mean, I did that ahead of time. But when you get to the laboratory exercises, you're doing it yourself. Then we move along to animations. Go to chapter 9. And we'll go to a topic here. And we're trying to show what happens when you take one signal and move it over another and see how well they match up. Okay? Sometimes you're doing it with the same signal, it's called an autocorrelation. Sometimes you're doing it with another signal, it's called a cross correlation. It's the way, for example, you might process a radar signal to figure out where the airplane is. Or it's a way that you can process other kinds of data to find out what's the distance to something, or where's the most likely place. There's several examples. There's one where I wanted to find out how long does it take from the time oil is drilled, to the price of the oil at the barrel head when it's drilled, to the pump when you go and get gasoline for the car. I wanted to see how long a price delay that was. And so I looked at an event that occurred, an event that jacked up the price at the wellhead right away, and I looked to see how many days it took before the price at the pump went up. And it's in here, it's in the book, it's a case study. So when you want to illustrate that visually with this kind of correlation, you do this. Very simple, but the calculation is being done, and you can see the result. As the middle signal is slid across the top signal. You slide them across, and at every point, you measure the area under the product of the two, and you can see where that works out to give you the maximum value, which is the place where there's a best match between these two. So that's the idea of using animations in here. That's a very, very trivial example, but you can go to chapter 7. Now, this is a study of the Langevin equation. The Langevin equation is really simple. It's the most simple equation when you're talking about Newtonian mechanics. You know, you've got a force, and you've got the velocity changing as a function of time, so that's the acceleration. So mass times the acceleration of the object changes as it is subjected to force and perhaps retarded by a viscous medium like water. Okay? But now if you have random signals feeding this, and the example of random signals is you have a tiny little object and it's being hit by water molecules. And the water molecules are from all directions, and the motion of the water molecules is the vibration due to temperature. Okay? And you want to study that. You want to know what's going on. That's what you're studying here. So that's what the Langevin equation is a case study. I go in depth. This is a very long chapter, and I go into excruciating depth, perhaps more than I should have, but I was having such a good time. So we get to this one, and then after equation 7.37, I got to zip on here. I'm sparing you all the math. You can thank me later. Okay, we're almost there. It's a gold particle attached to DNA, the double helix. The double helix is fastened at a base, and the thing's being hit by water molecules. So it'll start moving around, right? And as it moves, we can find the position in X, in Y. In fact, we can find it in Z. But we'll only record its XY positions of that gold particle here below. All right? And so let's see, here we go. And at every given time step, and you can see we're now in frame 90 or 100, it's making a different position. This is based on a simulation. I'll show you a movie of the real thing in a second. This is the simulation. We can make statements. Then, two protein molecules, Rec A, come and attach themselves to this DNA strand and change the mechanics of the thing. Like if you were running and I suddenly attached 2-pound weights to your knees, your run would certainly change. Well, that's what's happening here. And by studying what happens after this protein attaches itself to the DNA strand, we can get an idea of what are the mechanics of the DNA strand. How does it react? And how does it interact with proteins? And that was the function of this study. Okay? Those are examples of animations, and that's what you can do, and it's interactive, it's dynamic. Now we'll go look at films, movies. And to begin with, well, let's go here. What you're going to see now is a movie that was made in my lab where we had a tiny little gold ball, 40 nanometer gold sphere, 40 nanometers. Wavelength of light, blue light's about 400 nanometers, so this gold sphere is only a tenth of a wavelength. But within a dark field microscope, you can actually see light reflected back up to the eyepiece, and you can record that with a camera, and then you're getting the same kind of data that you saw in the simulation. And now you're no longer looking at the simulation of the top frame, you're looking here at the actual motion of this gold particle. And once again, I'm trying to bring home to the student who's studying this Langevin equation that you can deduce all kinds of things about the DNA molecule to which this gold particle is attached. So both the combination of animation and films. Now, I used films in a very different way in the beginning. One of the things I'll show you, hello. Come on. Sometimes this thing is slow to react. You know what I'm going to do? Go to here. Is one of the things you do when you're doing some of the laboratory experiments, I'm going to start those in a second, is I ask you to whistle. Okay? Now, this thing could, in principle, be, anybody all over the world can download the app to their, if they have an iPad or an iPhone. When we get to laboratory experiments, I'll explain, you don't want to do this on an iPhone, the experiments. The book, homework, that's okay. You need a bigger screen. You'll see why when we get to the experiments. But I realize that somebody on the other side of the world, when I say whistle, they might say, what's a whistle? Right? See, you got to be a teacher. You got to explain to them. So here's how we explain what a whistle is. Okay, so scene from a movie, To Have and Have Not. The woman is Lauren Bacall. She was 19 years old at the time. The man is Humphrey Bogart. It's actually quite a famous movie. This scene is a very famous movie, but it illustrates and teaches you in, I think, 22 seconds how to whistle. You put your lips together and blow. All right, that's what she said. So the idea is to engage the reader, the student, with the concepts that are going to be used. And that brings us, we have case studies. In one of the case studies was the Langevin equation. I showed you that already. One of them is predicting the natural climate, which will explain the cover of the book. So let me go to chapter 5. And here is a case study. I'm talking about random data. Air temperature is random. Air pressure is random. Okay? So I went to the website of the KNMI, Koninklijke Nederlandse Meteorologische Instituut, the Royal Dutch Meteorological Institute. And online there, any of you can get the data I got, which is weather measurements of air pressure and air temperature for over 100 years. Every single day for over 100 years. And so I did it. And here is the average daily air temperature, and here's the average daily air pressure for a period exceeding 100 years. I then went and I analyzed it, and I looked for structure in the data using the techniques that have been described in the book. Structure in the data. This is a case study. I found that in the air pressure, there's virtually no structure. But in the air temperature, there is a structure. And if there's a periodic structure, you should be able to see that with a Fourier transform. And this is the Fourier transform of the temperature data. And that peak right there says that there's a strong peak, okay? And that strong peak is at the spectral value 109, 109 out of 39,812 spectral values. That's the number of data samples I had, 100 years, 365 and something or other days per year, 100 days, 39,000 samples, peak at 109. That's 365.248 days. Sound familiar? From random data collected over a long period of time, you can estimate the length of the solar year. And how good is the estimate? That's a question that's dealt with in chapter 12, by the way. How good is the estimate? Well, the answer is that that estimate, I was about to push the screen up, but that doesn't work. There is an officially accepted value for that, which is 0.242 is the currently accepted value for that worldwide by scientists. And this one that I got was 248, so I'm only 0.002% above the internationally accepted value. And all I used was the average temperature daily thing recorded at this central weather station in the Netherlands. This is the correlation data. And there's that periodic cycle, which is 365.25 days long. And that peak up there says that if you correlate data with itself, you get the best match when there's no shift. But if you keep moving it over and it's periodic, then next time you get to the next place, there's then it keeps. So every 365.25 days, you get sort of a match. And that's revealed here. You can also ask the interesting question, for how many days does the temperature sort of stay correlated? Now, you can imagine that for over just a couple of days, it seems sort of random, but there might be a correlation, sort of the temperature tomorrow is going to be like the temperature today. And the temperature 3 days from now will be pretty much like the temperature today. But if you go 90 days from now, you'll be in another season. Temperatures won't correlate that well, will they? So you can ask the question, how many days is it until the correlation drops from 1, that's its maximum value, down to half? And the answer is 49 days. So for about 49 days on the average, temperatures remain correlated, 50%, they fall to 50%, and after that it goes down the tubes. You can ask the same about air pressure, and when you do, air pressure is down from its maximum value to about 50% after 3.4 days. The air pressure tomorrow will be roughly the same as the air pressure today. After about 3 or 4 or 5 days, it's another number altogether. The kinds of information that can be extracted from data when you have the kind of tools available that are presented in this chapter. Okay, then we have homework problems. Some of the homework problems are easy, some are difficult, and 2 are Olympic. Why do I call them Olympic? Because a couple times I was asked to write problems for the Dutch Physics Olympiad. And because I was teaching systems and signals, I had the opportunity to make up the kind of problems you always want to give every student, but didn't dare. But I could certainly put them on the Olympic thing. And here is, I'll show you just one of the Olympic problems, because one you might be able to want to think about. Problem 12.3. 2 notes on the piano, A and A sharp. Somebody plays a note, and you want to know which note did they play. What is the minimum length of time in seconds that is required to distinguish between the alternative? It's A sharp, or they played both notes together. And if you listen to them, and I synthesize them, they're not here in this thing. If I listen, your ear is not sure which it is. But if you have something like a Fourier analysis available, you can look at the frequencies and figure it out. But there's a certain amount of data you need, a minimum amount of data. And the question is, how much data you need to get the right answer? That's the point of this Olympic level problem. Very few people got this one right, I might add. Okay. So that concludes what I wanted to say about everything except the laboratory work. So let's go look at some of the labs, which might be the reason you came here anyway. So you press this, and you get something that looks like this. And you have if you want to record a sound, you click the microphone. If you want to play it back, you click the thing that says playback. And then you'll see the signal here. This is an example of recording sound that will be played back. This length of the sound is approximately 5 seconds. Okay? And then you go like this.
This is an example of recording sound that will be played back. This length of the sound is approximately.
Okay? So I recorded some sound, and then I can do this, and I can do this. I'm zooming and panning. If I zoom far enough out, then you see the reality of life is it's a discrete time signal that has been sampled. But if you are not zoomed out so far, it would be futile to represent all those little bars bunched up next to each other. You couldn't see anything, so I chose to display it this way. And I call this a continuous time display, and the other one was a discrete time display. You can also do that because, this should be fun. Okay, we're going over to chapter 2. Now I'm going to go down to the bottom. If you tap up at the top, it springs to the bottom. You don't have to always go and pick out that menu thing. So it'll spring to the bottom right away, which makes easy access to these kinds of things. This 2.1 is another experiment with sound. Let's do an experiment with pictures. All right, so here's a picture, and what I'm going to do is, this is just a placeholder. So what I'm going to do is do this. Okay, and I'm going to use the photo. Then I'm going to do this one and use the photo. And what you see down here below is the difference between the two images. Now, this part of the image barely changed. It barely changed. So if you subtract the brightness in the top from the brightness in the top, there's roughly the same. You get 0. That 0 is displayed here as middle gray. If the number is negative, it's displayed as black. If the difference is positive, it's displayed as white. But it's a color image. So you're getting 3 different, in the red channel, the green channel, the blue channel. Each one of those you get a difference. And you can actually look here. Now you're seeing just the red channel. Where in the red channel? Where that yellow line is. And the brightnesses only vary over a range from about -4 to +4. What's the purpose of this? Remember, what you haven't seen is they're being guided through the experiment with a series of questions up here and asked to think about what they're doing and why in this image down here in the red channel, why aren't they 0? What's going on? I mean, the ceiling didn't change. Okay? And you can say the same thing about the green channel. Oops. There's the green channel. Or you can do the same thing with the blue channel. Turn the other 2 off. And there's the blue channel. You can also pick another line. Like that. Now, why is this different here? Because I moved my head between the time I took the first picture and the second picture. That's why. All right? So this allows the student to explore the concept that even if there's nothing moving in the image, the 2 images are not going to be identical. And why is that? Anybody know? Noise. The noise in the camera. Room didn't change. The lighting. Actually, I saw a lamp flicker back there just a minute ago, but assuming that it's steady lighting. The idea, and you can do that with images, and you can do it with sound. Suddenly, you're doing laboratory exercises that can do audio with a microphone, or they can do video, or still images at any rate, with this. Let me do another one. How many of you have ever seen the book Where's Waldo or Where's Wally? You've never seen that? It's this picture of this little fellow wearing a red and white striped shirt, and he's lost in 1,000 other people that are all dressed up and walking around a shopping mall. And the question is, you're supposed to figure out where is Wally in this. And the reason I give 2 names, Wally and Waldo, is I think it's Wally in England and Waldo in the United States when you buy the book. Something like that. Okay, so here's this picture. And I call this, Where's Paulie? Okay. Paulie's in the right upper, you see that there where it says Paulie. And next to him is Schrödinger, and next is Lawrence, and next is Langevin. Okay? Now does anybody know about this photograph? This is from the 1927 Solvay conference, which was taken in Brussels on physics. And they're all here. All the great physicists in 1927 are basically in this photograph. Who's that? She won 2 Nobel Prizes. Come on, who is it? It's Madame Curie, right? And of course, we all know who that is because he's iconic. And here is Langevin. That's Langevin. Okay, now what I'm going to do is I'm going to say, where is Schrödinger? Okay, and you see this. What I did was I clicked on the photograph up there, and then I used that as a template and moved it across the image to see where I found the best match. And it came up with the best match in the image is here. Okay? And you can say the same for where is Pauli? Pauli exclusion principle here. But this is without any noise. How well does this work, this business of matching things up, if there's noise? Well, what you do is, there's some noise. Signal to noise ratio is now 50 to 1. And you ask, how well does it work? Has it done the, yeah. Okay, now let's see, can it still find, for example, Langevin? Yes, it did. Can it find Lawrence? Yes, it did. Now let's make the picture even worse by increasing the noise level. You can see the noise starting to come up in the image up there, and it's still finding Lawrence. Now the signal to noise ratio is 4 to 1. Can it still work? Can it find Pauli? Yeah, it found him at a signal to noise ratio 4 to 1. So this gives the student, once again, answering the kind of questions that are in blue here, the opportunity to interact with this. There's no camera, there's no microphone, so not everything requires the camera and the microphone. Sometimes it's just a self-contained laboratory experiment. I'm saving the best one for last. Go here. We haven't gotten even to that one yet, but all right. This one. Who knows what perfect pitch is in music? What's perfect pitch?
You hear a tone and you can tell what it is.
Yeah, actually, it's more than that. You can synthesize it. If I say to somebody who really has perfect pitch, and I've known a few people who have it, sing A4. That's 440 hertz. Sing it. They'll go, I can't do it, but all right. Sometimes I get good, I get close, but I can't get it. Do you have perfect pitch? So we're gonna test, okay? What I'm gonna do is I'm gonna give you a note. In this case, C6. C6 is 2 octaves above the center on a piano, okay? And this is the note C6. And the frequency of C6 is 1047 hertz, rounded off. Actually, it's got a couple more decimal points, but for this, that's good enough. I'm going to let you hear it, and then we're going to record your attempt communally, you can bury yourself in this, to reconstruct that particular frequency. So this is what it sounds like. Okay? Now I'm going to put the microphone on, and when I click on this, it will change its shape. And what I have discovered that the best thing to do is start whistling before I click. Otherwise, you take, and that's too late. It takes too much time, and that sound gets recorded too. So I'm going to count down. When I hit 1, start whistling. Okay? So 3, 2, 1. Okay? Let's see how good we got. That's where we came up as a group. Here. Everybody a little bit below the perfect pitch thing. And then you can do this with other notes. For example, here is a B5. Slightly lower. I'll give it a shot, see how well I can do. So the higher the note, the better I can do it. I can actually do C6 pretty well. Sometimes I do it so well. Ronald Lichtering, my co-author who shares an office with me, he's really surprised. I can sometimes get it right on the money, but not all the time. And then over here on the left, you can see the actual audio signal that was recorded in pink, and you can see the other signal, the pure one that's generated that you're hearing. So this is a test for perfect pitch, but it also allows you to explore several other issues like windowing of data, for example, whether you use a Parson window. I won't go into it. There's a whole bunch of techniques for doing good spectral estimation, and that's what this is really all about. One of the things I like to teach is the concept of accuracy versus precision. Accuracy and precision. People use those words interchangeably as if they're the same thing. Whereas accuracy has to do with getting close to the right value, and precision has to do with if you did it 20 times, you get almost the same number every time. They're very precise. So I made up a thing here. That's this one. Darts. The imaginary game of darts, the idea is to get the dart in the center. If you get the dart in the center, you're right on the money. Okay? So here's a person who throws darts. And we'll go up here and they'll throw about, I'll go a few more. They're throwing 47 darts. All over the map. Is this person accurate? If you take the average position of all these darts, it's in the middle. So they're accurate in that sense. Are they precise? No. This thing's all over the map. So accuracy and precision are not the same thing. The person who threw these, Jack threw these. Tobin, on the other hand, threw these. Is he accurate? No, he's systematically to the right and too high. Not very accurate, but is he precise? Yes. Okay? Yeah, I see the time. And this goes on. Okay, so here comes the last experiment. So this illustrates that kind of thing. The last experiment was specifically designed for MIT. Okay? We all know that image, right? You all love it. Dave, true story, Dave had a Volkswagen Beetle. Dave lived here on Bay State Road. Every day he drove here, up to there. On the way home, he came back over the Harvard Bridge and then came back down to here. What was characteristic of a 1959 Beetle is, here is the odometer on it. That's it. That is the odometer from a 1959 Volkswagen Beetle. There is no tenths of a mile on that. So the question is, how can you estimate, this is about estimation, the length of the Harvard Bridge by driving over the bridge using that odometer in your Volkswagen Beetle? And I give you two options. You can drive a fixed route every day, or you can drive a random route every day. And which one leads to the correct estimation, or an estimation at all, of the length of the Harvard Bridge? Now, we all know that you don't measure it in miles, you measure it in smoots, but that's another story. So what happens here he's taking the fixed route. See, he goes up to here. Now the measurement's going to start. The odometer starts at this distance, and now he's going to go over, and let's see what happens with the odometer. Yeah, it went up by 1 mile. Okay? If he does this again, now he goes back home. Now, if he does it again, now he starts his experiment, writes down the starting number and ending number. It goes up again. Every time he does this, it will go up. Every time he'll think the length of the bridge is a mile. We all know the length of that bridge is not a mile. The other hand, if he runs a random route, starting from his home, where I also lived. It's one of the houses from the fraternities. See, he went off on a random route. He probably went up to Elsie's to get a sandwich, for those of you who know what that was. And then he gets back to here. Now when he goes over the bridge, he gets a number. Hey, it didn't increase. On this particular traversal of the bridge, the number on the odometer didn't change. The next time he did it, it's a random route. Watch him, he goes over here, makes a left turn, goes up, God knows where he is, comes back from the other side, comes back to here, records it, 22 and 22. Sometimes it switches over, sometimes it doesn't. And I'll leave it to you, by closing this talk, to think about under what conditions will it switch, and how could you estimate the length, and how many times would you have to drive over the bridge to make a good estimate? And then I point out, in a modern Volkswagen Beetle, this is the odometer. And then it gives you the distance in tenths of a mile. Thank you very much. Thank you.
You have to probably turn off the camera, but if people want to ask you questions.
Does anyone like to ask questions?
We have the room for another half an hour if people want to do popular.
Yeah.
You chose to implement the text, it's a tour de force of programming and education as well. But why did you choose to do it as an app as opposed to an interactive web page? Pages. Or am I seeing in your app really a browser that's embedded in there? You mentioned JavaScript in passing, for example.
It is. We use a browser. There is a browser in here, and in theory we could put it up on a web page, but then you can't control it. It's to say money. The answer to your question is money, right? Now, isn't that base of me? But if we put it up on the App Store and it's free, people can still not download it and give it to a friend. They can tell a friend about it, and the friend can download it and use it, and it's fine and it's free, and that goes on for a while. But we have recurring costs. We have to pay €100 a year to renew our Apple license to work on the App Store. We have to pay money to the domain name every year. We have to be able to recoup. We have to buy new iPads every once in a while. We figure we're going to need an income stream to be able to support this project for a period of time. And so when all of the laboratory exercises have been implemented, then we will go over to a paid model. And if you're asking what will we charge for this sort of thing, the answer is between $10 and $20, which is not a lot if you compare that to the cost of a textbook, say at the Coop. So it's enough to cover the costs we have of developing and maintaining all of this work. Furthermore, we've done it on the iPad, and I've had a huge number of people say, when are you going to have an Android version? Okay? The answer is we do. We have a version that runs on Android. The problem is that it's excruciatingly slow on the Android platform, and we don't know why. We're still working. Same exact software, same exact environment. We just flip a switch and say, put this on the Android, don't put it on the iOS. And okay, puts it on the Android. And then the change in speed is a factor of 10 to 20. Now you saw those Fourier computations here when I was, well, you didn't know there were Fourier computations maybe, when I was matching up the pictures of Pauli and Schrödinger. There's a whole bunch of Fourier processing going on in the background. And those were taking less than 2 seconds. On an Android phone and on an Android tablet, it's been between 10 and 20 seconds. That is so long that it's not viable. But it must be possible to do it faster, and there's something we're missing here, and so we're working on it. But the reason we're not doing it, if I just did it as a web page thing where you said log in and so forth, I don't see any way of maintaining control over that with respect to the costs.
It can be monetized, but
Yeah. Any other questions? Yeah.
When you were thinking this up, did you have any examples to draw from to look at and figure out what you liked, what you didn't like, or is this all de novo?
As far as we know, the first. This is a premiere. Since then, in fact, because of the xTalk, somebody sent me an email and said, I heard from someone who heard from someone, et cetera, et cetera. We're holding this summer in Chicago the first workshop on interactive textbooks. Would you like to come? You're invited. All right. I thought that's great. I'm from Chicago. I didn't know you were. I don't know if we'll go. Probably not. But it's clear that it's an idea whose time has come. And the fact that I think this is the first one that's available on an app store, pretty sure that actually, it does not mean other people aren't being active in the field and aren't in parallel developing what we're doing. Whether we'll have any influence on how they do it or what they do, I don't know. That remains to be seen. Yeah.
If I'm working on one of the problems and I need help, how do I get help?
Well, presumably you've been working. A teacher tells you to buy a textbook, and tells you which homework problems to do, right? Okay. That teacher told you to buy this textbook for $10 to $20, told you which experiments to do, which homework problems to do, so when you have a problem, you go to him or her. Don't come to me. I know what you're getting at. I mean, can you imagine? I don't, that's one of my problems with this online video education, is students have questions, and there's one poor person out there who's got 10,000 students, and they all have burning questions that have to be answered by Monday because they have to hand in homework. You know, and the only person they can turn to is, that's a non-viable model. And you can say, yeah, well then just make an answer book and make that they can go check the answer book. I know how young people work. I've been teaching long enough. Okay. Thank you very much.
Thanks again, Ted.
Okay.